Hi, everybody. We're here to present human algorithmic interaction using a large language model, augmented artificial intelligence clinical decision support system. So first, to give you a little bit of background about this research project and the study we undertook, I first want to give a little bit of background information on large language models, which are positioned as a technology in the healthcare field that can provide value to clinicians, specifically through clinical decision support systems. Clinical decision support systems are tools that clinicians can use to help them make difficult and challenging clinical decisions. To our knowledge, there are no studies that evaluate usability of large language model-based systems for active clinical workflows in a team-based clinical decision setting. In our study, we use a model of upper GI bleeding to create a large language-based AI clinical decision support system. We use upper GI bleeding because it's a clinical model with a clear risk stratification paradigm. It's well-defined, guideline-driven medical treatment. Clinical decision support systems are used widely throughout clinical medicine, and AI-CDSS have started gaining traction, not only in research, but also in clinical applications. Large language model-based AI-CDSS are just in their infancy, and there's not much information about how users will choose to interact with them when they actually use them. And we're going to deploy our study in a medical simulation environment, which allows the testing of new technology in a safe and controlled environment.
The study we present here is part of our simulation center project. In this study, we're exploring how healthcare teams use large language models, augmented CDSS, in simulated patient interactions. We are analyzing feedback and data from these simulations to identify what drives or hinders the use of the AI CDSS. Ultimately, we aim to discover how to best design AI CDSS that fit seamlessly into clinical workflows, enhancing care without adding complexity.
And then we'll move on to discussing the methods of our project. So what we tried to do was develop a risk prediction machine learning model trained on data from patients in a large hospital system who had upper GI bleeding. And we introduced an interactive dashboard to visualize that risk and GutGPT, a large language model trained on GI guidelines for upper GI bleeding. And to test this new technology we developed, we designed a randomized controlled trial to determine how physician and medical student teams interact and use these systems. And we deployed it in a simulated medical environment. So for a bit on exactly how the study was designed, our participants were randomized into clinical teams that resemble the clinical teams that are seen in a medical and clinical environment of 2 to 4 participants each. And these teams had medical students, emergency medicine residents, and internal medicine resident trainees on each team. And then the team as a whole was randomized to either using the GutGPT large language model interface with the interactive dashboard, or in access to the interactive dashboard along with any other internet tools they desired. And after that first randomization, the teams would complete 3 risk stratification focused simulation scenarios, after which they took a usability survey. The team is randomized again to either GutGPT or the dashboard only, and they complete 2 clinical management-based scenarios. After the completion of the trial, every participant is interviewed individually by members of our research team using a semi-structured interview template. And now we'll look at some images that give you a better idea of exactly how the simulations looked. Starting from the top left, we have the control room in our simulation suite, which allows controlling of the vitals, patient scenario, and the patient mannequin that is used by the residents and medical students. Next, you get a visualization of 2 residents interacting and speaking with the simulated patient mannequin and the EMR setup that's right next to the patient. Next, you see the GutGPT terminal, which the senior member of the team uses to interact with a GutGPT large language model. And then our last 2 images, you have the vitals control program and the simulated EMR, which have high fidelity with actual real clinical environment, which immerse the participants in the simulation and also let them interact with the electronic health record in a realistic method as they would in a hospital environment.
Here is a screen recording from our simulation session. So there are 3 tabs on top. Under Use the Model is a dashboard where clinicians can access patients' conditions and adjust them to get updated risk predictions. And under GutGPT is a chatbot where the user can ask questions and get answers using natural language. Here are some statistics about our participants. By the time of paper submission, we recruited 31 participants, and they were placed into provider teams of 2 to 4 in each simulation trial. And there's a total of 12 provider teams. The recruitment of the study continues, and the presented number of participants did not reach the threshold for statistical power analysis, which means the quantitative data we presented later are not tested for statistical significance, but rather an indicator of the general trend.
Now we'll move on to the results. We'll first start on some of the qualitative data we gathered from the interviews. So after the interviews were completed, our research team used rapid qualitative analysis methods, analyzed the interview data, and compiled a research board with quotes and key insights from the interviews with the participants. And we elicited several themes that we'll highlight in this presentation. On usability, many participants indicated that ease of use of the program was influenced by their familiarity with other similar programs, such as this internal medicine resident who says, I immediately knew what to do when I started using it. It's just like ChatGPT, indicating familiarity. Another important consideration for many participants was the text output GutGPT put out. As you just saw in that video, sometimes these responses can be a little bit lengthy. In time-constrained clinical environments, many residents and medical students prefer actionable guidelines that sometimes are very brief. As two emergency medicine residents note, puts out large blocks of text at time, especially when citing sources. Takes a while to read through. And I like the response. However, I can see myself saying this is taking too long to read on shift. And I don't think I would do it for every patient, but I would do it for patients I'm a little unsure about. Another key aspect that many participants elicited was that any tool, any clinical decision support tool they would use must be integrated into electronic health record naturally. So medical student noted, I thought it made GutGPT very different than existing clinical prediction tools because I don't need to input every detail myself, because they're already incorporated in, and it makes me more comfortable that I'm able to use such information. As another medical student indicates, I think it could definitely help. I feel like it would probably be dependent on its integration into Epic, indicating that electronic health records are the way that medical information is disseminated and actioned on in the modern clinical world. A clinical decision support system, especially one that uses AI and large language models, must be able to act within that realm. Another interesting point that we noticed was that many participants wanted to use GutGPT as essentially molded GutGPT to their own workflows. Many residents and medical students are familiar with the GBS calculation, which stands for Glasgow-Blatchford score, a risk stratification tool for upper GI bleeding. As an internal medicine resident said, it's easier to go into MD Calc and do a GBS calculation rather than using GutGPT if it's going to say, well, this is what GBS means, but we don't actually have the data to pull, indicating that many of these residents and medical students wanted to use tools that are familiar to them and were frustrated when GutGPT didn't have that functionality that they desired. Next, turning to human-computer interaction. An important aspect of medical teams in real clinical environments, it's team-based nature, which are often hierarchical depending on the experience of the many people within the medical team. In our study, the teams were separated into senior and junior members in the clinical team, with the senior members more responsible for using the tool and making executive clinical decisions, while junior members were more responsible for information gathering, such as interviewing the mannequin and gathering laboratory data. A junior internal medicine resident notes, I was focused on the patient, so I didn't get a good look at the GutGPT system, but it seemed like a useful response from my brief look. This reflects the different roles that senior and junior members have in a clinical team, indicating that senior members of the team in a real clinical scenario would be more likely to use AI-CDSS, and it may be useful for it to be tailored to them. And on the perspective of using GutGPT in a team or as a lone practitioner, internal medicine resident points out, typing into the chatbot takes you away from the primary focus of the patient. I would only use it if I'm part of a team for that reason.
In addition to our interview data, we administered an system usability skill survey to understand the user experience with GutGPT. We asked participants to evaluate the system after they finished the risk scenarios. We note here that this portion of data collection was added later, resulting in 22 available observations out of the 31 participants. And we didn't administer the full-length survey. Instead, we only selected 4 statements for the sake of brevity. The 4 selected statements are, I saw the system was easy to use. I would imagine that most people would learn to use this system very quickly. I find the various functions of this system were well integrated, and I felt confident using the system. Participants expressed their opinions on GATGPT's usability on a 5-point scale, ranging from strongly disagree and strongly agree. Let's look at the results. The feedback on GATGPT's usability shows a general trend of agreement across 4 statements. The average attitude scores are all positive, with users held more positive opinions about the system's ease of use and learnability, and less positive opinions about the system's function integration and their confidence in using the system. This result shows the initial indication towards the positive perceptions of GATGPT's usability. Here comes our third type of data. All conversations between GATGPT and participants were automatically recorded. Here are some example user inputs to our chatbot. These prompts are of varying lengths and varying formats. Some of them include patient conditions, and some of them simply ask about, should I admit this patient? We perform an analysis on this conversation history. First, let's focus on how often participants engaged with the chatbot. The data shows that on average, there is a higher frequency of prompts in content scenarios, 3.9 prompts per scenario, than in the risk scenarios, where only 2.4 prompts per scenario. One possible explanation for this could be the nature of the tasks. In risk scenarios, the participants only need to determine whether to admit the patients. In the content scenarios, they have to make management decisions. This potentially leads to participants to seek more guidance from the chatbot. In the context of risk scenarios, scenario B stands out with higher frequency of the prompts. This can be explained by the fact that it is a borderline case, where the medical data isn't clearly pointing towards admission or discharge. It's also important to consider that the sequence in which the scenarios were presented might act as a confounding factor to the results present here. Having first been exposed to risk scenarios could have increased the participants' familiarity and confidence with the system, and thus leading them to prompt more in the later content scenarios. The general trend holds same for the medical students and resident physicians, suggesting that the level of medical education did not significantly alter the reliance on the chatbot for decision support in these simulations. Now let's examine the prompt length. Our findings show a higher average word count per prompt in the risk scenarios, resulting in 15.3 words per question, compared to the content scenarios, only 11 words per question, suggesting a more detailed inquiry in the former. This pattern holds true regardless of the clinical expertise of the participants. However, a closer qualitative look suggests that users tend to provide a detailed patient background in their initial question, but follow up with more direct queries and do not repeat information. Consequently, the shorter average word count in the risk scenarios would simply be due to an increased number of the follow-up questions. Based on our insights from our data, our study highlights 3 design principles for LLM-augmented AI-CDSS. The first is comprehensive usability focus, stemming from user feedback on difficulties with complex interface and data interpretation. This principle suggests that the enhancement of interpretability, good user guidance on how to interact and what to expect from AI-augmented CDSS, and seamless integration of the current model and the system, for example, like EHR components, are of equal importance for a strong AI-CDSS design. The second principle is customized deployment strategies. This means the implementation of AI-CDS into healthcare settings should accommodate the varying medical specialties and specific needs of different users within the healthcare ecosystem, giving the different perceptions of the model's usability from our participants based on their medical specialties. And the third principle is understanding and navigating team dynamics. Designers should recognize the impact of team structures on AI-CDSS use, and thus design for adaptability and offer targeted training. Thank you so much for listening.